Today we're here to talk about the changes to the 2015 Canadian Electrical Code and how it's going to apply for the arc fault circuit interrupter changes and potentially how changes to how you're going to be wiring up residential houses going forward. Basically, this wanted to give you some background why these changes have come about. So even though we've implemented a lot of changes and the 2012 code has branch circuit arc fault, we're still experiencing quite a few residential fires that actually occur in the branch circuit wiring. So when we're looking at these statistics, we actually have still quite a few electrical fires that can be attributed to fire starting from the branch circuit wiring. So we realize that there's still some improvements we can make to the technology and to help make these homes safer for property damage and for personal loss of life. So that's what drove these changes. So the electrical industry is continuing to make improvements in electrical safety. We've gone from knife switches all the way up to the current technology. We're introducing new things, which is this combination arc fault circuit interrupters. So you can see it's been a slow changes, but we're continuing to change, and the adoption of these continue to take some time, but it's all with the goal of improving home safety. So when we're looking specifically at arc faults that occur in a home, we classify them into two types. There's lots of operational arcs, which are the switchings of loads on and off. So these arc faults we call operational arcs. When you close a contact, they come together, you'll get a slight arc. When you flip a light switch, you'll get an arc. So these are all operational arcs. They're normal in a system. So they're not the ones that are the potential for the damage. It's the non-operational arcs, or the potential fire hazards that occur when there's damage to the branch wiring or to the electrical connections. These hazardous arcs are what we're really looking at when we're looking at this AFCI technology. There could be damaged cords, loose connections, that sort of thing. So there's lots of examples of operational arcs, and the technology's been improving over the years to classify and identify these things. The skill saws, the vacuums, all the motor loads turning on and off create these operational arcs with unique signatures that in the past may or may not have caused nuisance tripping with some devices. But this technology is at a point today where all of these operational arcs have been classified, and we won't get those tripping for these operational type of arcs. So the examples of the non-operational arcs that are the hazardous arcs, which we're really designing this technology to detect to make the home safer, are when there's damage to the wiring. When you get these the wires get punctured by a staple or a nail, you get the animals chewing on the wires, you get exposed conductors, and you get arcing from those conductors to ground or to line, etc. So you also get arcing with bent or crimped cords or loose connections, or a broken conductor. So the broken conductor is actually a loose connection in a way. So they're sitting end to end, and you'll get an arc on that point as well. So brittle or aged cords, stuff that's plugged into your system as well. So those are the hazardous arcs that we're trying to detect. So there's lots of drivers for this: temperature, humidity, mechanical stress, voltage stress. As the system ages, you'll get lots of opportunity for these loose connections, corrosion, animals chewing on the wires, etc. So there's a lot of opportunity for these non-operational arcs to be introduced into a system. So during the lifespan of a home also comes into play. During the construction phase, you're pulling all the wire and running all the receptacles. The cords can be damaged. At that point, you can typically see it and identify it, but once the drywall's up and all the furniture is moved in and all the cabinets put in, there's a whole phase where damage can become to this branch circuit wiring. And as the home ages again, all of those degradation drivers come into play with the voltage stress, heat, temperature, humidity. So the whole point of this is there's a lot of opportunity during the lifespan of a home where damage can happen, or these potential arcs that can cause fires can occur. So that's what's driven the change to the code and the improvements to the arc fault circuit interrupter technology. So I want to take a look at that for a second. So the types of arcing faults we're looking at are these high current level parallel arcs and also these low current level series arcs. So the parallel arcs are what typically we've been looked at with arc fault circuit interrupters and branch circuit wiring. Those we're looking at the parallel arcs from line to line, line to ground, those things, so the parallel version of the arcs. So the other type of arc is this lower current series arc, and it's an arc fault that occurs at lower levels, but there's still a potential for that to cause a fire. And that's actually a loose connection or a break in a conductor. So that's what we call it. In series with a connected load is the series arc. So when we're talking about the codes and standards, the recent changes have come into play to address both of these types of arcs. So this is the actual excerpt from the 2015 Canadian Electrical Code. So this is how it's written. So each branch circuit supplying 125 volt receptacles rated 20 amps or less shall be protected by a combination type arc fault circuit interrupter. So when it says combination type, what it's referring to is that combination of the parallel arcs and the series arcs. It's not a combination of arc fault, ground fault. That's not what they're talking about with this terminology. So we're kind of referring to that arc fault, ground fault as a dual purpose or a dual arc fault, ground fault, and we're getting away from the use of that combination in relation to that, because the code is written for these series arcs and parallel arcs when you're talking combination type. So you can see that first statement does not talk about bedrooms or sleeping facilities. It's talking about each branch circuit supplying 125 volt receptacles. So that's one of the biggest changes you'll see right away. So that obviously is going to be expanding these use of these arc fault circuit interrupters, and also changing the type from this branch circuit or only looking at parallel arcs to this combination type AFCI, which is looking at the parallel and series arcs. So there's some exceptions obviously as well. So the receptacles installed in accordance with some other rules in the code, these rule A and B, rule 26.712, those are like the counter workspaces, the independent circuit for the fridge, if there's other GFCI protection for bedrooms, that kind of thing. They're accepted from this new change to the code. I think that's probably where some of the confusion will come. But basically your kitchen circuits or work surface receptacles, and we're only talking about receptacles here, not lighting, right? We're mentioning receptacles, so this is where you're plugging in your devices. So the whole point is now we're protecting the branch circuit from these parallel arcs, and also the connected or plugged in equipment from these series arcs. So we're talking about the receptacles where you're plugging these devices in, the lamps and the toasters and the microwaves, that kind of thing. Some pumps are also excluded, provided they're on an independent circuit. That is the only device on that circuit, then you don't need to use an arc fault circuit interrupter on that device. So there's a few exceptions where you don't need to use them that you'll need to get up on. And notwithstanding this, it's also introducing a new device that's now written into the code. So an outlet branch type arc fault circuit interrupter. So an outlet branch circuit type. So now we're going into the OBC outlets or receptacles. So now this is introducing the use of the outlet branch circuit interrupters or the receptacles into the code as well, provided that they use them in a specific way. So the wiring method for the portion of the branch circuit between the branch circuit overcurrent device, the breaker, and that first outlet shall consist of a metal raceway or armored cable. So we'll see why that is in a second. So this is just an overview of what the change could mean. This is not written in stone. It's just to give everybody an idea of the change of scope of where these arc fault circuit interrupters are going to apply. Previous with the 2012 code, you were just looking at the bedrooms, so the areas in green up here. So the way the new code's written, we just kind of figured where some of these exceptions are going to be and left them white, like the kitchen work surfaces, the bathroom counter spaces, the laundry room kind of thing, that already have the GFCI protection would be exempt, and potentially the garage as well if those circuits are on a GFCI circuit. So obviously there's a big increase in the scope of the use of this arc fault circuit interrupter technology. And again, this interpretation is going to be up to the local authority having jurisdiction, how they interpret those exceptions and the rules that apply to this. So basically, the 2015 code for the AFCI requirements is an expansion within all the dwelling units, and it's the extended coverage to the receptacles and other than just the bedrooms. So typically this will include now your living rooms, your hallways, your closets, rec rooms, that sort of, all of those spaces, the living spaces. It also has expanded AFCI options. So the combination type AFCI circuit breaker, so it introduces combination type, which is a new series and parallel arcs, and it also introduces the AFCI receptacle, provided that it's installed at the first outlet box of the branch circuit. And provided you use an armored cable for that first run, which we'll see some more in a second. So when we're looking at both of these technologies, an AFCI circuit breaker is designed to protect the entire circuit from the panel and all of the connected loads. So your series and parallel arcs are protected from the load center forward with all your connected devices. An AFCI receptacle can only actually protect your downstream wire from the parallel and series arcs. But from the upstream from that AFCI receptacle to the panel, it's only protecting from series arcs. So the higher current parallel arcs would not be protected in that run. So that's why they wrote into the code that home run from that first receptacle to the panel needs to be protected by the armored cable to protect against the potential for the nail being driven into it, the staples, etc. So to prevent that or minimize that risk of those parallel arcs occurring during that portion of the branch circuit wiring. Obviously, I'll take a second to look at both types. There's advantages and disadvantages to both. So a combination type arc fault circuit interrupter, so this is the breaker of the combination type, installed in the load center is going to protect the entire branch circuit, including the connected devices now that we're looking for these series arcs. So the advantage, you're protecting the entire circuit from the source. Disadvantage is that the legacy load centers may not accept breakers, or we're actually not designing breakers or AFCI breakers for these legacy load centers. So obviously that's a big disadvantage in using the AFCI technology. We're only designing it for the current product. When we're looking at the OBC AFCI, or the outlet branch circuit AFCI, you're looking at that armored cable between the standard thermal mag breaker and that first receptacle in the run, which is permitted now, but that first receptacle has to be easily accessible, and so this is how the code is written for using the OBC AFCI receptacle. So the comment from our ESA representative here is that they're currently allowing the use of this, and specifically when there's an older load center that you can't get an AFCI breaker, this is a great solution. And even though the implementation of the code isn't mandatory yet, they are accepting the use provided you wire it in this fashion, correct? So the advantage of that is it allows up for a local AFCI reset, right? So it's just like the GFCI, there's the button if it trips. You don't have to run down to the load center to reset it. It's a local point of reset. There's a price advantage over an AFCI receptacle versus a thermal mag breaker combination AFCI. There's more stuff in the breaker, right? It's still a thermal mag breaker, thermal magnetic. So it's tripping on overcurrent and all of that fun stuff, plus it's the combination AFCI. So there's a price advantages over an AFCI receptacle. The disadvantages is the installation of that armored cable for the home run. And that could be costly depending on where you place it, but again, you could place it right next to the load center with a short run of conduit in some cases. So the disadvantage also is that AFCI receptacle must be located at the first outlet so that you can be protected for the whole circuit and be readily accessible. So I think that's going to be a point of interpretation by some inspectors. What's readily accessible? Is in a closet readily accessible? Behind the couch readily accessible? That kind of thing we'll need to clear up as we go to implement this code. So that location of that first receptacle is going to be key in how you're wiring up the home now. So it can really change how your wiring practices are going to be going forward. So that AFCI receptacle must be placed at the first outlet. So, and we're only looking again at receptacles. We're not looking at lighting. So now you might be running separate lighting circuits versus receptacle circuits. So the wiring practices could really change when we're looking at the implementation of this code. So our message up here is, well, Eaton is the only manufacturer that actually makes both arc fault circuit interrupters and the outlet branch circuit receptacles. And we actually share that technology for the arc fault sensing between our wiring devices division and our load center breaker division. So our message is that there's no right way when you're looking at implementing these changes. You use the method that works best for the solution. So for the example, if it's a legacy load center, you can't get the breakers, obviously the OBC receptacles are the way to go. But in other cases, if it's new wiring and you want to avoid the use of that armored cable, then put the AFCI breakers right in the panel if it's like new construction. So there's cases where both make more sense. So it's really up to how you guys are going to wire the house, what makes most sense, which one you're going to use. The question is, why aren't the lighting circuits included with the code? They actually looked at that, putting the lighting circuits as part of the requirements as well. But with the changes in the lighting technology and the LED lighting and the low voltage lighting and that technology has been changing at such a rapid pace that there's been really a disconnect between us as like the thermomagnetic breakers and AFCI guys and all of the noise and things that these systems introduce on the systems. So I don't know how much you guys have been familiar maybe with some of these high-end lighting systems and that convert down to DC, and there's pretty loose, well, I won't say loose standards, but the manufacturer of these things don't actually meet any kind of standard yet that's implemented. So it's really hard to marry those two technologies and to ensure that you're not going to get nuisance tripping, that kind of thing. So they really exempted the lighting circuits just due to that fact that a lot of new products are being developed on that side, and we don't know how that's going to interact with the AFCI technology. And we kind of want to lessen the pain. If they're plugging, the question I guess if there's a light that they're plugging into one of these AFCI receptacles, would there potentially be an issue? I think in those kind of systems, the risk would be low, as they're not really that intelligent. They might be converting the AC to DC for the use of that light, but it's not a system-wide thing. And those do exist now, and us as Eaton as a company has not got any feedback that our AFCI technology is incompatible with the current stuff on the market. It's worthy to note actually here that this combination AFCI technology has been adopted in the US since 2008. So the technology has actually been around since 2002. It was only adopted in the US in 2008. So it's a pretty mature technology for the combination AFCI. And because they've implemented in the US since 2008, there's been a lot of years of testing of this stuff and working out the bugs in terms of all this nuisance stripping. So we have a pretty bulletproof product at this point. So the question is the arc fault receptacle being available in a dead front model. And I'll turn that over to Mark.
Currently the arc fault's not available in a dead front. We're not probably going to be making it. It's being discussed as a possibility, but I doubt we're going to launch it as a dead front. Partly because the reason that you're going to want a dead front receptacle is so you can put it beside the panel, correct? So when the 2015 CE code is fully adopted, you will see a number of circuits, as you saw in Tim's presentation, the number of circuits in the house that need arc fault presentation is going to grow immensely, right? So if you put dead front receptacles beside the panel to cover all of those circuits, you'd end up with a half a dozen to 12 dead front receptacles lining the wall beside your panel, and that's not visually practical, and it's not typically practical. So The dead front receptacle, as opposed to a GFCI dead front where you might have one, and it seems to make very good practical sense, going forward, the dead front receptacle for AFCI doesn't make a lot of sense, so the demand on it is going to be 1 out of every million receptacles made is what we're getting as requests. As Tim said, the AFCI code changes in Canada come typically after the code changes in the US. So the US adopted similar code changes as we're adopting in the 2015 code last year across the states. And so we're taking a lot of data as far as demand and what receptacles and breakers we'll be selling going forward from that information that's coming up out of the US. And there's very, very little demand once people understand how much arc fault is required in a home. Very little, once you have a full firm understanding of that, very few people actually want to go with a dead front. It's a great question though, thanks very much. Does that help answer your question? Thanks so much.
Well, the arc faults you're going to be using in bedrooms different than the arc faults you're going to be using in the rest of the house. And the answer is actually no. The arc faults in the bedrooms are going to be the new type as well. They're going to be the combination AFCI. So the code doesn't talk about bedrooms at all. It talks about all receptacles. That includes the receptacles in the bedrooms. So going forward, those breakers will be combination AFCI instead of branch circuit AFCI that they are now. Yeah, well, the nuisance tripping, again, in that branch circuit technology has been greatly improved as well. I would say from any breaker made from 2009 on would be substantially improved for tripping things like the vacuums and the skill saws, all of those things. Even ham radios, believe it or not, were identified as a source of RF noise. The neighbor turning on his high-powered ham radio, in one case that were actually 2 or 3 cases we found, tripped the neighbor's circuit breaker because the RF frequency that it introduced into the home's electrical circuit looked like an arc fault. So we actually redesigned the technology in the breakers to look for that as well. So it's actually a continuing process where the engineers are looking for improving this product and improving the arc signature. So if you get that case where that bedroom circuit is tripping on the vacuum, if you put one of these new combination type AFCIs in, 99% that'll go away. So the question here is, why don't we just put the AFCI into the main panel and protect the entire house by protecting the incoming breaker? That's actually a great question that's been thought about in the industry for a while. The biggest problem is that if you did plug in, or if you got that loose connection somewhere in the home, it's going to kill the power to the whole house. So the advantage of having it on each branch is that branch circuit goes down, not the entire house. Right? So now you'll be able to identify, oh, the problem is on this circuit, rather than if the whole house goes down, you're going to have to figure out, well, why did the whole house go down? So there's a lot of advantages to protecting the branch circuit wiring versus the whole home. They're looking at some technologies where you can look for an arc fault in the whole home and have like some indication, but without any trip, maybe like an audible alarm or things like that. So the question is, if there's a main circuit ground fault protection on the main device, how is that going to affect the downstream AFCI, correct? There is no conflict with GFCI. It's 2 different things that they're doing. So using them in combination with each other is not a problem. There's no technological issue with that at all. So having ground fault circuits on an arc fault protected circuit is no issue. So, and vice versa. They're looking for different things and they don't affect each other. Are smoke detectors going to be required with arc fault protection? Or
if they get put on, if they just by chance get put on a circuit with arc fault?
Yeah, there should be no issue with a smoke detector on a circuit with arc fault either. So the question is, what's the difference between the arc signature for like a light switch or a vacuum motor starting and the actual arc faults? The actual answer is there's not a lot of difference. But what the breakers are trained to do is one arc when something is turning on, or a couple within that milliseconds, is acceptable. So if it sees 4 or 5 in a row that exceed that time limit, then it goes, hey, maybe now there's a problem. So there's different ways. So even though the arc signature is very similar, it's looking for the typical cycle of that turning on and off and starting on and off. So it doesn't trip on the first signature, it'll trip on the fourth or fifth. Now it sees it as a recurring problem, right? So even though the arc signature actually looks very similar, that's why it's been an interesting technology to develop these breakers. So there's been a lot of lab work with the looking at the millisecond changes to the 120 volt sine wave. The question is there any testing equipment for arc faults? And to my knowledge right now, no, there's not. The arc fault technology, we've shared all of our signatures and our tripping with the testing guys that build the testing devices. Eaton doesn't make them, but we've shared our technology. So, hey, if you want to make a device to test these, here's our signatures. So even when we introduced the branch circuit a while ago, it changed the technology and the breakers got smarter. The arc fault testers on the market didn't keep up with that technology, and the arc faults, the latest technology didn't recognize that as a true arc, because it's not a true arc, it's just a test indicator. So right now, as far as I know, there are no AFCI testers on the market that will be compatible with this technology. So the only way to test it is to press that test button.
That's meant to test the actual receptacle trip, whether it's a DFCI or an arc fault. The true way of testing it is to test the trip circuit, not just the
Correct.
test button.
Yeah, so the comment was the true way to test it is to use the trip circuit, not plug in an AFCI tester. And actually there's a self-test incorporated into these designs as well. So you don't have to press the test button to test the circuit, it's continually self-testing itself. So if it does find a problem, it will trip itself. So the comment was if there is a problem in the circuit, it may be impossible to troubleshoot what the actual cause is. And that's a good question, because the AFCI technology we're actually implementing as Eaton actually has a diagnostic LED built into the breaker that'll give you either 6 trip codes or 7 on the CH line, because one of our products has some ground fault testing greater than 30 milliamps, so not people protection, but it actually looks for ground faults as well. So it'll actually give you the reason it tripped, right? So now you know the branch circuit or that it tripped on, right? So first thing, you unplug everything, see if it's something that plugged in that tripped it. Second is, from the closest to the farthest, you can figure out what the problem is. But these diagnostic AFCIs, which are standard in what Eaton's launching for this combination AFCI technology, has an LED, so the test button is clear. And it'll actually blink a pattern to tell you why it tripped. Was it an overvoltage? Was it a series arc? Was it a parallel arc? So if it's a series arc, you're looking for a loose connection. So there's actually built-in technology to assist with identifying these causes. Do we have more questions? Yes, sir?
You guys figured out the lifespan of these AFCI receptacles?
So the question is, we figured out the lifespan of these? I guess the question, or to answer that, there is no, with the UL standard, with all of the standards that go into these, I think it's 10,000 uses or something that we have to test them to. So I know on our CH line, we guarantee them for life. If there's ever a problem with that circuit breaker, you just bring it back and exchange it. On the BR type, which is our other line, it's a 10-year guarantee or 10-year warranty. So, but the life of it should actually be more like 15 to 25 years. I mean, it's like any electrical device or mechanical device. These things are heating and cooling, right? So over time, these voltage stresses, heat, humidity, all of these things are factors. So even the electrical system in a home, the wiring has a life. People aren't really aware of that fact, right? So they think, oh, my load center's been here for 50 years, it's fine. But the heat and stress is metal, heating and cooling, contracting, expanding, all of that fun stuff. It's gonna have a life cycle. There's gonna be all of those degradation drivers on that as well. So all mechanical and electrical devices have a lifespan. The question is, does this apply to the hotels, motels, nursing homes, etc.? We definitely does apply to the residences for nursing homes, if it's your residence, right? Actually, we were discussing earlier about the hotel, motel part, whether it's considered a residential unit, and it's really not. So as the code changes roll out, those interpretations will be made and addressed. And we're looking at what, May 2016 for adoption and for the enforcement of these changes to the CE code. In Ontario. The question is, are the breakers affected by cold weather? Yeah, so if it's installed in a garage, etc., obviously it would be colder. UL and CSA testing requires them to be tested to -20. So they're good to -20. They haven't been tested below that. But just in application, any breaker, and you guys will know this, that's conducting current is going to be warm. So if there's a load on any of that system, typically the main breaker is definitely a little bit warm, and that in turn keeps the panel warm. So if there's no load on it, that could be an issue, but we've never experienced anything that I've got feedback on about low temperature affecting these breakers.